Okay, let's start out. Happy Friday, everybody. So it looks like it's going to be a good weekend. Hopefully you can get outside for at least a couple minutes. We're going to start with where we were last time, where we ended up. I'll just remind you that the problem we're working on is we see data from some normal distribution, so some Gaussian distribution, and I see n IID sample data points from that distribution. In statistics, we don't get to know what the parameters are of the model. It's at least the paradigm we're working under, that maybe we know the distribution that creates the sample, and we want to learn its parameters. It's a fundamental breakthrough in thinking that people did about 100, 150 years ago. People started thinking about this. It took a while to catch on. Now, there's a lot of distributions. It used to be thought that there were maybe 4 types of distributions. Pearson was saying stuff like that. And the name of the game was to figure out the parameters for those distributions. It's not that simple. There's a lot of distributions out there, and they arise for different reasons. So right now, I'm kind of just mechanically showing you how Bayes operates. I'm not teaching you how to model. So I have this big fiction that we know what F is. We know what the sampling distribution is. Later on, we'll be talking about how to build model, and we'll see specific applications where these distributions appear. Normal distribution appears all the time. We use normal distributions all over the place. Somebody help me to understand why that's such a special distribution, and why we invoke normality all the time.
Naturally occurring.
What's that?
Naturally occurring.
Naturally occurring. Nature has given us this distribution. Somebody help me understand that. Like, it's this formula, 1 over square root 2 pi sigma e to the minus 1/2 squared residuals xi minus mu squared divided by sigma squared. Naturally occurring. Yeah, please.
I was going to say central limit theorem.
Central limit theorem. That is it. You know, I can kind of understand, like, people think, and I've done this before. You know, where it's like, maybe you just think of it intuitively, that you say, hey, there's some distribution around some point, mu, and it kind of like tapers off. You know, the noise tapers off as I get farther and farther away from it, so it's concentrated in there. That's kind of a intuition that a lot of people like. Maybe it's symmetric to the left and to the right. Central limit theorem says a lot more. It says this particular functional form of how things decay as you move away from mu. And that does occur naturally. What do you do to a sample so that that transformation of the sample is normally distributed? Central limit theorem says what? It says averages, regardless of the distribution, so long as that average has a finite variance, the average is normally distributed if n is big. Okay, so that's a place where we always see the normal distribution arise, if we're studying averages or something like that. I didn't do anything asymptotic. I'm just saying the data points themselves are normally distributed. So anything that's like an averaging process, when we see data out of an averaging process, if that averaging process is IID, then we see normality. And so there's all kinds of stuff in nature that are just kind of amalgamations and averages. Under other conditions, weighted averages can be normally distributed. I have to talk about how those weights are picked. In cases where things are not IID, sometimes we see limit theorems that limit to something normal as well. And so we see it across the board when we're averaging across things. There are cases where you don't see the central limit theorem applied, so like a Cauchy distribution or something like that. Samples from a Cauchy distribution, if you average up, they're Cauchy again with the same parameters. So you never reduce the variance, something like that. So high variance, or I misspoke, Liang's like variance. There's no variance in that model. So you can't reduce the variance, there is no variance. So there's spread, but it's not that mathematical thing we know as variance. So anyway, just a little bit of a precursor. We do see normality all the time. I use normal mixture models all the time. So if I have things that have multi-modes and stuff like that, there is a theorem out there that says that if I can mix over normal distributions, I can represent any smooth distribution. So it's kind of like what Fourier said a long time ago. That if I have a signal and it's relatively smooth, I can use sines and cosines to recreate that thing. So this is a basis function a lot of times that we use. So studying things that are normally distributed is very important. So this is our second example. We did the beta binomial example. That's when you have success or failure with some probability you want to estimate that. Bayes was useful because when the sample size is relatively small, or if p is small or something like that, Bayes does pretty well. And you're studying that on your own. Okay, so this is the problem that we're studying right now. We've set this whole thing up. I'm actually going to ask you to do this whole thing right here on your homework. This is the one that you're aiming towards. I've kind of given you the answer. So if you just write down what the posterior distribution is, it's likelihood times prior, and then I normalize everything. So this whole thing right here is the normalizing constant. It's a function of x, not of mu that we're trying to infer in the first place. So we want to build this posterior distribution. I'm layering in another fiction that you know what variance is. So we're just starting easy. The likelihood looks like this. We're going to end up letting n be 1 in our example. And on the homework, you're going to play around with n arbitrary. Not much change. Math is about the same. You're just going to have this sum that's going to roll up into the exponent there. You have to do a little bit more algebra. So I wrote down Bayes' theorem like this. I said, hey, this is likelihood times prior, but I took this functional form right here. It's the joint sampling distribution. In the IID case, that's just the product over the fx's. And then I'm going to multiply it by this prior right here. This is my prior distribution. Something to notice is that the random variable that we first observed was xi. So it appeared over here on the left-hand side, the traditional way to write down a normal distribution. And these were the parameters. My prior distribution is putting a distribution on mu. So that's acting as my random variable. And it's going to be centered at some hyperparameter mu naught in some hyperparameter. Sigma naught squared is going to explain the variance in that prior. We'll have to discuss how to pick these. So let's get the answer. Let's look at what the answer is and then discuss what is the impact of those hyperparameters. Okay. So again, I'm going to do this problem with n is equal to 1. There is a reason I do this, and you'll see that reason in about 2 lectures. N is equal to 1. For our example, so pi mu, our posterior distribution, sampled on our one observation, I'll call it x obs. So that's our one observation. And the statistical gods has told me what sigma was. Thank you. That was helpful. So, and then I have my prior distribution. I usually write down pi mu, but perhaps you might write down it's conditioned on mu naught and sigma naught. And if you wanted to write that down, I would probably thank you for it. Tell me what your hyperparameters are. Discuss them. Don't hide them from me. Don't make me ask about them. Tell me why you picked them. So if you don't do that, nobody's going to be too satisfied. So they want to know how you pick these, what the impact is, and you as a Bayesian are supposed to describe that to them. A lot of times I just write this down as pi mu. Okay. So and that's how most people probably write it down, just to save some space. There is an assumption, since I'm building the posterior conditional on sigma squared, if I don't use sigma squared here, I'm saying my prior information is independent of sigma squared. So there's no information in there. So I'm not including it. There's no sigma squared, so I'm not writing it down. If you wanted to write it down and then say it's conditionally independent, people would probably understand that without you telling them. So I kind of like to explain it over and over again in class. And so our posterior distribution is going to be proportional to, oops, I don't know why I did this. This is likelihood times the prior, and this would be pi mu given x odds and sigma squared. Now I haven't been entirely polite because I didn't write down my hyperspecification here. If I were being really pedantic and I was a really tightly wound mathematician, I would insist that you write this in there as well. Most people don't write down the hyperparameters here. So they just write it like this. Sometimes they'll even confuse you and take out sigma squared from the notation. What you have to do is you have to look at the right-hand side of the equation and see if they use sigma squared. So I'm going to write it in there for you. So this is going to be proportional to, I can get rid of all my normalizing constants and everything. Again, n is 1, so there's no product. I don't need to write that stuff down because it's all known and it's constant. I've already written this down up to proportionality, so if I write proportionality once, and then I write equal later on, it's still proportional to the answer. If you want to carry all your normalizing constants, you can do it. Your answer will work out the same. It won't help you too much. It'll just cost you a lot of ink and time. But maybe you want to do that. This is e to the minus x odds minus mu squared over sigma squared e to the minus 1/2 mu minus mu naught squared over sigma naught squared. And I got rid of my normalizing constant there. Once I threw away one of them, I should throw away all of them. So we recognize this. We've said this for 2 lectures in a row. This is a normal distribution. Why? Because it's e to the minus in quadratic form. Those are normals. Can't be anything else. So this is e to the minus 1/2. And I'll just write it out as its quadratic form. This is going to be x obs minus mu squared over sigma squared plus mu minus mu naught squared over sigma naught squared. I have to recognize what distribution is this. I'm just going to do a little bit of expansion for you. I know that this is a function where the variable, the random variable, is mu. So I'm interested in mu in all of this. And so where mu appears should tell me where this thing is centered and what the spread looks like. So this is just going to look like this. E to the minus, and I'm just going to collect some terms real quick. So I'm going to, well, let's just do the expansion really long the first time. And later on, we'll be able to do this faster. So this is going to be x obs squared minus 2 mu x obs plus mu squared over sigma squared. This is all in the exponent. Plus, do the expansion. This is going to be mu squared minus 2 mu times mu naught plus mu naught squared divided by sigma naught squared. Now again, I know what sigma is. I know what sigma naught is. I know what mu naught is. And I know what x obs are. So those are all my constants. So I'm just going to give you a little bit of visual on what the constants are. These are going to be constant terms. And let's say the big circles are going to be terms involving mu. mu in there. So let's just look at them. This one is constant. This one is constant. We do have the sigma naught and the sigma, but they're always wrapped up in mu. So I'm not going to circle those one way or the other. I'm just going to tell you to hold on to them. But my terms involving mu are going to look like this right here. There's going to be this one. It's going to have sigma squared attached to it. There's going to be this 2 in front of here. So this is supposed to be a circle. Let's make those amoebas. And then I have this other term right here. I'll just write a 1. And it also involves sigma squared. Over here, constant term. And just like the other thing, terms involving mu are that. And then this, you'd like me to write down a 1 right there and that thing. Okay, so let's just keep an eye on those. I want to tell you some stuff about normal distributions just really quick. Usually we write down a normal distribution like this. So just aside. I'm going to let z, this is just a new random variable. So let's not think about this example for a second and we're just thinking about some random variable. It's going to be normally distributed. So z is normally distributed, mean mu and sigma squared. We'll use the typical parameters. So what that means is that z given mu and sigma squared is going to be equal to 1 over square root 2 pi sigma e to the minus 1/2 z minus mu squared over sigma squared. That's a normal distribution. I know where it's centered here. And it has a spread that's determined by sigma or some function of sigma. So sometimes we like to talk about the standard deviation, sometimes we like to talk about the variance. You know one, you know both. So I don't need to look at this part to figure out what sigma is. If somebody wrote down this number and just computed a number for me, I'd have a hard time recognizing what sigma was. I'd have to know what square root of 2 pi was. I would divide that out and get you sigma and invert it that way. I could find it there, but it's all the information is in here. This is the kernel of the distribution. So this is my kernel. That has the shape information. Everything else is just normalized and constant. So if we wrote it like this, in this nice condensed quadratic form, it's easy to recognize where mu is in sigma squared. This, I could chisel away at this and make this thing look like that. And I learned a technique in high school for doing that. It's called completing the square. Okay, and so we've all done it. It's not that hard. You just have to remember what quadratic forms are. I'm going to reverse that technique. This is exactly completing the square backwards. I'm just going to look at what the expanded squares look like, and then I can recognize what the terms are. So I'm going to expand the square. So this thing is going to be proportional to actually, let's just write it here. So still aside, this is going to look like f of z given mu and sigma squared is going to be proportional to, and I'm just going to think about the kernel, e to the minus 1/2 give myself some more room. I'll write this really big. Fz given mu sigma squared is proportional to e to the minus 1/2. I'm just going to expand out that quad. So this is going to look like z squared plus minus 2z mu plus mu squared. And all of these are divided by sigma squared. Sigma squared. Sigma squared. Sigma squared. Let me just ask and make sure we're on the same page. What is my random variable here? Z. So not mu, Mu is our random variable in this problem, because we did base. Flip the thing around. Z is my random variable. So this is the quadratic term, right here. It's always going to appear in a quadratic, otherwise it's not a quadratic. If it wasn't a quadratic, it wouldn't be Gaussian. This thing is Gaussian, it's got a quadratic term. And how I recognize the variance is I always pull my -1/2 out front. So I always soak that thing out here. And then I think about whatever it's multiplying by, and whatever that term in front of the quadratic is, the inverse of it is the variance. That's my algorithm. I look for the quadratic term, I take whatever's multiplying out in front. So the quadratic term is 1 over sigma squared, which is 1 over the variance. So how I find variance is I end up taking the quadratic term and I invert it. One over sigma squared inverse is equal to sigma squared. We're going to apply that same logic over here in a minute. So I get the variance first. Then I go and I look for the mean. The mean is always tucked next to the -2 linear terms. So the -2 linear term always has an entanglement of the mean with the variance. But if I can find the -2 linear term and I know what the variance is, I can isolate the mean. I can recognize it real quickly. So instead of completing the square, we just learned an algorithm for recognizing what the expanded form looks like. That's what I do. So I don't go and complete the square on this. It'd take me 10 extra minutes to solve the problem. So the -2 linear term so I always have this -2 right there. I never get rid of it. We'll have the -2s over here. I've got the -1/2 tucked away. So I always write it into this form. And that's going to be mu over sigma squared. So what I do is I take that -2 linear term and I multiply it by whatever I found right here. So the expectation, another word for the mean in this model, the expectation is my -2 linear term and I take it and I multiply it by my variance, what I found right here. Seems like a lot of work, but it's going to be very useful right here. So this is going to look like mu over sigma squared times sigma squared is equal to mu. Well, so it's just another way of seeing the exact same thing. And it saves me a couple steps in this problem. So what this says is, if I'm trying to find what is the mean of this thing, where is it centered, and what is its variance, I need to find the -2 linear term, and I need to find the quadratic term. And then I'm done. So let's just do that. I want to just point out, I can factorize this out. So everything's coming in an additive form through an exponential, so it factorizes into a product. So I'll just do this once, but I'm going to do this step almost every single time instantaneously. So this is e to the -1/2. I'm going to rewrite this. This will be exact equality. And so this is going to look like mu squared. I'm just going to isolate my mu squared term. It's right here, and it's right here. So I've got this multiplied by 1 over sigma squared plus 1 over sigma naught squared. My -2 linear term, -2 mu. It's right here, and it's right here. So I'm just going to write that down. This is going to be x obs over sigma squared plus mu naught over sigma naught squared. And I'm going to close this up and just write down another thing. I always just drop this term real quickly, but there's this extra stuff. There's these constants. They have nothing to do with mu. E to the minus 1/2. I've got x obs squared over sigma squared plus I've got mu naught squared over sigma naught squared. So this is equal to that. All my actions right here, terms involving mu. This has nothing to do with mu, and so I just get rid of it. And I change that to a proportionality sign. We've been throwing away normalizing constants all the way through and just looking at the shape of likelihood times prior. That shape is determined by this. Okay, now let's apply our algorithm. Not hard. Where's the variance? It's this thing inverted. I look for my quadratic term. I've got my minus 1/2 factorized out. Quadratic term, invert that thing. So my variance, and I'll be specific, this is for my posterior distribution on mu, which is the mean, so it's the variance of the mean. You can get your head around that. So given x, given sigma squared, this was our posterior distribution we are after. This is going to look like 1 over sigma naught squared plus 1 over sigma squared. Guess I can put it in the same order. Inverted. I'm going to leave it like that. I kind of like this form. You will see books combine the denominator and write it down. So it looks like the way they wanted you to do it in 3rd grade or whatever. They say, no, you're not supposed to leave things like this. It should be over a common denominator. Let's leave it like that. I like the way it looks. My expectation of mu given x in sigma squared is going to look like this thing multiplying by my minus 2 linear term. So it's right here, and I've already compartmentalized everything really nice. So this will look like, give myself a little bit more room, x obs plus mu naught. This is over sigma squared. This is over sigma naught squared. That's my minus 2 linear term times my variance. 1 over sigma squared plus 1 over sigma naught squared. Inverted. So there's my answer. So I would complete this by writing down the full-blown answer and remind you that this is a normal distribution. And so based off of this one data point, here's what I think the answer is. So pi mu given x sigma squared, we know sigma squared. In this one, this is going to be a normal distribution. It's going to have a mean. I'm going to call this pi e mu given x in sigma squared. I could call it e star or something like that, but I'll just be more specific. E, and I'll tell you what the random variable is, just to be polite. There's so many running around this problem. And then I would end up telling you the variance as well. Call this variance of mu given x sigma squared. So this would be e mu x sigma squared. So I fully described the distribution to you. This posterior is a normal distribution with this mean and this variance. The only thing we haven't discussed is what's mu naught and what's sigma naught in all of this. I just want to think about this answer for a second. So a lot of times, humans like to think about means. Why? There's a lot of different types of averages out there. Means usually are determined by central limit theorems themselves, things like that. It's on a unit scale that we can usually think of, the same scale as the data. And so it's the central tendency of the data. And so we kind of like thinking about that. So this looks like this. Mu naught over sigma, I'll do it this way. Mu over sigma squared, mu naught over sigma naught squared. And I'm going to just write it a little bit differently this time. 1 over sigma naught, sigma squared, plus 1 over sigma naught squared. So this is a weighted average. So it's just a weighted average. It's a weighted average between, oops, I'm sorry. Nope, this is x odds. I saw puzzled eyes.
Shouldn't it also not be squared?
Yeah. All kinds of craziness. Boom. Yeah. That's it. Okay, all kinds of craziness happening in the middle right there. So glitch, we're fixed. This is a weighted average between the observation and the prior mean. And it kind of makes sense. And you'll see this form in engineering. People do this and make weighted averages just like this. And they'll say, well, let's match it. And if you want to explain that, you might be a Bayesian and explain it like this when you take a weighted average between things. And so it's nothing fundamentally new, but the Bayesian answer is a little bit different than maybe the frequentist answer. So just real quickly, what would an MLE give you back? What's the MLE? It's x odds. So just if you want to check. The maximum likelihood estimator, if I maximize that likelihood function, it's x odds. So they just give you x odds back, and the Bayesian weights it with the prior. So this prior is kind of tugging on it. How much weight am I putting on mu naught? It's determined by this parameter. Right here, 1 over sigma naught squared. So I'll just write down real quickly some notation. This is called the precision. So it's not the variance, it's the inverse of the variance. And that has a name. It's called the precision. So sigma squared is the variance. 1 over sigma squared is the model precision. One over sigma naught squared is the prior precision. Sometimes people will call the sampling distribution the model. Now I usually think of the model as that times the prior, but just so I'm on the same page as everybody else, usually people call F the model. So that's okay. So model precision. And usually we give this a name. Most people use phi. So I can call this phi naught. So this is a weighted average where I'm weighting over the precisions of the model. So if the variance is very large, 1 over something very large is very small. So I'm very imprecise. There's a lot of variability. If the variance is very, very small, the distribution is p, and I'm very precise. That's where the naming comes from. So, precision. We're going to be using that convention in our next problem. So I think that's kind of what I want to think about, is how much impact are we influencing our answer. So we're directing everything towards mu naught, our prior mean. That's where we're centering our answer. And if I knew something about the process, maybe I would be willing to put in a value for mu naught. But without telling you what the problem is, you're kind of lost. I have no idea what x is even measuring. So I'm not even sure what I should anchor everything towards. So, but your answer is being regularized in a sense. It's being penalized. It's being dragged by the prior. So if I wanted to make the precision infinite, I could do that. So I could drive down all of my prior variance. I could make my precision, I should say maybe 0 or something like that. I end up not being very precise in how I specify my prior. So if we think about our prior, this is going to be pi mu given mu naught sigma naught squared. It just looks like this, where it's going to be centered at mu naught. This is a function over mu. And how peaky this is around mu naught, we'll imagine those stacked on top of each other, is determined by this parameter right here. And so if I made that bigger, the answer might look like this. Really flat. Doesn't look Gaussian, but you get the point. Turn the tables. So very flat through here. This would be coming down a lot more than I'm illustrating, because it'd be so wide and the area under that curve should be 1. So I could make this wildly big, this number, and basically I wouldn't be penalizing very hard towards mu naught. I would say it could be anything. So some Bayesians like to take a limit over these things and think about limits of conjugate priors. And so you might be inclined to think about what happens if I think about the limiting sequence of priors. If you're a mathematician, you'll like that terminology. If you're a probabilist, you'll like it that way. But if you're an engineer, just take a limit, you know, or just take this thing and make it 0. You might be thinking of plugging it in just like that. That's a big problem if you're a mathematician, so they like to think about you're limiting to that, but you never actually get there. So maybe it's a psychological trick, but it does work. And we can study properties of things that maybe work. So let's just think about that. If we take the limit, so remember our variance, mu given x sigma squared is going to be 1 over sigma squared plus 1 over sigma naught squared inverted. If I take the limit, is sigma naught squared goes to infinity, or I could think about v naught goes to 0, the precision parameter. It's the same thing. This thing goes off to infinity, that's at 0. Invert this thing. Now I did grad school limit taking. You probably want to do that the way they taught you to do it in calculus class. I'm just going to limit through. So we can see that thing goes to 0. So this thing is going to go to 1 over sigma squared plus 0 inverse, which is sigma squared. And our expectation, we can do the exact same thing. Expectation of our posterior, this is going to be x. It's over here. So what happens when I take this limit? Nothing funky happens down here because I've always got some positive thing. Same thing happens here. This is going to go to 0. That's going to go to 0. If you don't like that, do L'Hopital's rule. So if you want to go through it very formally, that's fine. So I can just see it working out. You can apply that. But you can see nothing weird happens right here. I'm always anchored next to something. I'm always anchored next to something, so those disappear. So this is going to look like x opt over sigma squared plus 0 over 1 over sigma squared plus 0. And this is going to be equal to x opt. And our variance is sigma squared. Now, if you're a classicist and you like doing fiducial statistics, and you've already just inverted the likelihood without thinking about the prior, this would be your answer. Most Bayesians would say none of those steps are justified. But basically, if you're building a confidence interval, you'd be doing something just like this. If you're in Stat 101 class, you didn't know anything about Bayes, you built an interval that's centered at x ops, and it would have standard error. It's the square root of that thing. Multiply that by 1.96, and so you would be using these parameters in exactly the same way the Bayesian might. So not a super impressive answer, but kind of interesting to think about. I will tell you, just real quickly, if we had n data points, so this is your homework problem, your answer would look like this. Expectation of mu given all of my data. Sigma squared. So that thing is just x1 and xn. This would look very, very similar. Instead of centering everything around x ops, everything would center around some of the xi's divided by n. That's x bar. What would the variance be? It'd be sigma squared divided by n down here. I would have my prior, mu naught, sigma naught. So it'd be a weighted average between these things. And I would divide by 1 over sigma squared over n plus 1 over sigma squared, naught squared. So this is the answer you will get for your posterior mean on the homework problem. Same answer, really. I'm just dragging across sums everywhere. So how much weight are we putting on things? Let's just think about this as a function of n. The prior is static. It doesn't have anything to do with it. It's just your prior. Here's what I thought. Regardless of how much data you see, you shouldn't be changing your prior thinking, because that's supposed to come before you see the data. If you include the data in there, there can be all kinds of stuff that goes on. We'll talk about that later in the class. But basically, as n gets bigger and bigger and bigger, this number is getting bigger. The n flips over to the top. Same thing happens here. And so I'm becoming more and more concentrated around this answer. And everything is pulling away from this. So if I ended up making this fairly diffused, right here, so big, this would be small, and as n got bigger and bigger, I put more and more influence on what x bar is converging to. So you see this Bayesian sort of central limit theorem appearing. The effect of the prior is wearing off. So again, just a weighted average. I want to just say one thing about this before we move on. Think about it over the weekend. I used to be a little bit uneasy about this. But if we let sigma naught squared goes to infinity, are we allowed to do that with the normal distribution? Plug in an infinity into that answer? It makes this normal distribution go from something that's peaky to something that's flatter, flatter, flatter. So this thing right here is e to the minus 1/2 mu minus mu naught squared over sigma naught squared. So as sigma naught goes to infinity, this thing goes to a 0. E to the minus that thing, it's going to a 1. Constant. So it's a constant function between negative infinity and infinity. So it's starting to look uniform. And you cannot integrate a uniform between negative infinity and infinity. It will blow up. Jenny?
So what is the
What is the practical?
So I know this is a probability distribution that has some elements.
Yeah.
Does it mean that the probability of occurrence of any variance in that list is wrong?
I will help you to think about that. It's not the probability of every element. It's not a probability at all. But the weighting on every element is uniform. So the weighting is the same. The word I'm changing on you is probability because there is no probability anymore. So if I had something like this is the kernel of the distribution. I'm just missing the normalizing constant. If I tried to normalize this between negative infinity and infinity, minus infinity to infinity 1 d mu. So this right here is starting to look like pi mu. That's at least a normalized version of this. I'll try to irritate my calculus teacher one more time and say that. It's infinity. It blows up. I need to take a limit of those arguments and show that this thing is converging toward infinity. But this is unnormalizable right here. So this prior that we just picked, pi mu, is improper. Which means it blows up. It's not normalizable. Now Jenny pointed out an important characteristic, that I'm putting equal weight across the full continuum between negative infinity and infinity. And maybe you like that. And maybe you think, I don't really care if my prior is a probability distribution per se. What I care about is my posterior, because that's where I'm doing my inference. I'm not doing inference off of the prior, I'm using the prior as a tool. And so if you did this, your posterior would be sigma squared would be, and let's just think about this with the n being this thing right here. So if we did this, this would be a normal distribution, x bar, and this would be sigma squared over n. This is the answer that you're going to work out on your homework. So if I didn't take this thing to infinity right here, I'd still have this term right over here. If we were dealing with this problem with one data point, x bar would just be the sum of one element, which would be x obs. I'm giving you a lot of different answers here that you need to think through. But the posterior still exists. So the posterior is a proper distribution. This thing is proper. Even if I just had one data point, I'd be centered around x obs, n would be 1, my answer would be sigma squared. So that would be 1, that would be sigma squared. It's still a distribution, so the posterior is proper. So I'll give you something a little disheartening, that a lot of priors that we use are not probability distributions. They're limits of probability distributions. And they try to not put too much mass in one place. So if you didn't know anything about mu naught, why put any mass on that? And so the posterior does need to be proper though. You like Bayes because it gives you a probability distribution. You like to interpret things on a 0-1 scale. You like belief intervals. You like saying, I think the parameter's in there. You can still be a Bayesian and use improper priors. Here's my big provocative question. Is that Bayes' theorem anymore? Is that what Bayes said? Bayes said something about probability distributions. And if I did take sigma naught to infinity, I'm kind of using the format of Bayes, but I'm not applying it to probability distributions. If you feel better about saying, well, but you're doing it on a limiting sequence of distributions. If that makes you feel better, that's good. You know? So you take enough measure theory classes, you'll go, yeah, that makes total sense. It's an abstract concept. You know, in an engineering sense, it's what Jen just said. I took a equally weighted penalty across mu and penalized the likelihood with it. And that kind of makes sense. So if you don't like thinking about limits of probability distributions and you like thinking about weighting the likelihood, and that's your interpretation, that's fine too. I can move between any of those. I've got comfort through all of that. We're going to come back next time And we're going to work on this problem. I'm going to say more about this later on, about invariance properties. But later on, next time we're going to come back and we're going to find this. Sigma squared, given mu. So I'm going to switch the roles of mu and sigma squared. I'm going to learn sigma squared given I know what mu is. And I'm going to start off simple and I'm going to assume you know one data point. We'll end up coming up with something very similar with different distributions. Our conjugate prior will be inverse gamma on this. I'm going to fix that force by inverting the parameter so I can place a gamma prior instead. I'm going to change the convention. So I'm going to put the prior on the precision. We'll take a limiting sequence of those distributions, see what the improper form of the conjugate prior is. The conjugate prior will be gamma in that case. So the mathematics will be a little bit different, but the spirit of everything will be similar. And then we're going to try to figure out what the joint distribution of everything is. And we're going to think about that joint distribution and what the impact of our prior is. Once we get through these steps and we kind of understand how Bayesian operates, I'll show you all the computational stuff. That's it for now. Have a great weekend. And I'll see you on Monday.